Hi guys. So sorry I've been out with COVID. I'm going to so if my voice sounds a little scratchy, I'm sort of recovering from it still. What I want to talk about today is the next sort of move. We talked about in the previous chapter about power series. We talked about analytic functions. We talked about the Cauchy-Riemann equations, and all those involve ideas about differentiation. Um, in viewing complex analysis as an extension of real calculus, we need the other half of the picture, which is the integration half. And so what we're going to be talking about is what integration looks like in a complex analysis setting. And to begin with, just as in the calculus of several variables, we had several different notions of integration. And there were area integrals, iterated integrals, contour integrals, surface integrals, and whatnot. We have to nail down the particular notion of integration that we're going to use here. And so we're going to use contour integration as the basis for our exploration and definition of integration in that setting of complex analysis. So in complex integration, integrals are defined over curves. So we're talking about contour integrals here. So the idea is that we want to create an object that we can use in real calculus. So remember that in the sort of basic integral of real calculus is an integral over an interval. So when you write something down like the integral from a to b of f of x dx, the vision that you should have in mind here is that you have a one-dimensional space that you're integrating over. So you starting at A, and then you travel along some parametrized path to the point B, and really what you're doing is you're traversing that interval. You can think about this as it's a chunk, it's a line segment that you're starting at the point A and ending at the point B. There's not a lot of different ways to do that because you're in a one-dimensional space, and so there's like the obvious way to do that is with a line that goes from A to B. In fact, that's what the dx here represents, is that you're just basically moving with unit speed from A to B along the one-dimensional line that starts at A and ends at B. To talk about the same sort of integrals, so like one-dimensional integrals in a several variable setting, you need to have a notion of integrating over a curve. And the way that we do that is with parametric equations. So we have to have some curve. So you can imagine that if you have a point A and a point B, and you want to define what it means for a function to be integrated over that curve, you actually need to come up with some way of writing down the function of that curve. So for us, we're going to think about these things as points z is equal to x plus iy, some curve, where we have x is a function x of t, and y is a function y of t. And normally we choose a parametrization from, say, 0 to 1 if we can figure out a way to do it, if it's natural. Other possible parametrizations run through, say, angles, and so there might be a's and b's that correspond to polar angles. However we do it, the basic idea is that x of a, I should be careful here because we're using a and b for time and also for space. So imagine that we've got a point z0 and a point z1 for our beginning and end here in the complex plane. The idea is that at time a, we're at the beginning, so x of a, y of a corresponds to the point z0, which is x of a plus I, y of a. And then we have a point x of b, y of b, corresponding to z1, which is x of b plus I, y of b. The idea is that we've got some function that gets us from here to here. So as we traverse the path, we start at the initial point at time A, and at time B, we're at the end point. And the functions that we write down actually get us the curve that we're after. And that's what we mean by this. So a smooth curve is the graph z is equal to x plus iy of some parametric function where the x coordinate is given by x of t and the y coordinate is given by y of t, and then for some fixed interval of times, a to b, and then we want the curves not to be jagged or bendy or have weird jump discontinuities. We wouldn't really think of that as a curve. And so we add the additional condition that these functions are continuous and have continuous derivatives. And that's what we mean by class C1. So essentially, a smooth curve is a curve with no corners in it, is one way of thinking about it. Continuous functions can be really nasty. Functions with continuous derivatives can't be. Okay, so what we're going to do is we're going to take the notion of a parametrized curve and use it to build a theory of line integration. So it's good to have some examples of parametrized curves here, some pretty standard ones. If you have a point, say, z naught is equal to x naught plus I y naught, and z1 is equal to x1 plus I y1, and you want to build a parametrized graph or function that gets you from z naught to z1. So you can imagine here's z naught, and here's z1. And what I'd really like to do is to build, say, the straight line path from z1 to z2. So here we're thinking about straight lines. Then the easiest way to write down the parameterization that gets you this is to put yourself at z naught at time 0 and put yourself at z1 at time 1 using what's called, I guess it's the standard sort of convex combination. So you would write down something like z of t is equal to z naught plus t times z1 minus z naught. And that is where t runs between 0 and 1. Now, it's obviously linear because that has this sort of linear form, right? We've got a point plus a variable times another point, or if you like, a vector. So this is the sort of vector equation of a line. And at time 0, it's easy to check. It's z of 0 is obviously z naught, and z of 1. Well, what happens at z of 1? We put the 1 in for t. We've got z naught plus z1 minus z naught, which is z1. So this is sort of your standard straight line parameterization. I'm sure you've seen this before, at least in multivariable calculus, probably at the end of the first year calculus sequence, and then again at least once in your second year calculus. But it's a nice way to be able to quickly throw together a line segment that connects two pieces. The other sort of standard graph that's nice to know is circles. So circles and pieces of circles come up all the time. So if we have a circle and we're trying to parameterize it, the easiest way to do that, imagine you've got a point z naught, and you have some circle of radius r that you're trying to trace out around z naught. This is one of the most useful kinds of contours that comes up in the study of complex analysis. We'll be doing a lot of these. The way that you build those is with a standard sort of sine and cosine type setup here. And so you want to do something like x of t is equal to x naught plus r times the cosine of t, and y of t is equal to y naught plus r times the sine of t. And that's the sort of standard R2. You think of this as being the R2 version of a circle, parametric equation. You can always take a sort of two-variable parametric equation and make it into an equivalent complex parametric equation by writing it in sort of real plus imaginary part form. So z of t is going to be equal to x naught plus r cosine of t as the real part, plus I times y naught plus r times the sine of t. And that's the complex version of the parametric equation. And here, if you want the whole circle oriented in the positive direction so that we're traveling around the curve in the correct way, and we'll talk about orientation more in a little bit, here we're going to let t go from 0 to 2 pi. And that will start us here, and then we'll wrap this way around the circle. So counterclockwise is normally chosen by default to be the way that we want to traverse a closed curve like this. Okay, so there's the end of a little reminder about contours and parametrizations that's going to come up. So once we have that, we can define the notion of a contour integral. So if we have a smooth curve C, say starting at a point Z0 and ending at a point Z1, and let's suppose that we've got a graph that describes this curve. So this is called C for contour or curve, and C is equal to the graph of some parametric function z of t. Then we can define what it means to integrate a function f over that curve just by composition. So it's like we've got f defined everywhere on the complex plane, and then we're going to restrict it to the curve by just feeding the curve into it. And this is the way we do that. So the integral of over c of f of z is just defined by the chain rule. So this is the standard move in several variable, or when we do parametric integrals over parametric equations or line integrals in multivariable calculus. You plug the curve into the function, and then you have to multiply by this z prime dt term, which is that's how you do composition when you're doing these line integrals. If you like, where that comes from, just to remind you, is that if you know that c is z of t, then that means that dz has to be equal to d by dt of z of t, which is equal to z prime of t dt. Right? This is the sort of standard change of variables formula. So we're restricting the function, we're doing change of variables. Now, of course, these are complex functions, which means that we can expand them out into real and imaginary parts. And so what this is supposed to be is sort of the extended z replaced by x plus iy, and then the derivative of z is just x prime plus iy prime. And that move right there justifies why we set it up this way. Because even though I can't show you in the formula, at this point, I have a complex function of just one variable, t, and that means it can be sorted into a real part, which will have no i's in it, and then some parts that have imaginary parts running around, where I could factor out an I. And since I can sort that function that's inside here, so this f of x of t plus y, iy times x prime plus iy prime, that can actually be written as, you can think the integral, if we call this function, say capital F is equal to f of z times z prime of t, this function can be sorted out into a real part of f plus an I times an imaginary part of f. And that means that the integral can be sorted out. The integral of f dt can be thought of as the integral of the real part of f dt plus I times the integral of the imaginary part of f dt. And these pieces, so this piece and this piece, those are both real integrals. There's no complex numbers in there, right? The real part and imaginary part of a function are real functions. And so complex line integrals break up into two different real valued integrals, which means that we can use the theory of real calculus to study them. So let's look at an example of how to do this, a very simple example. So let's look at the integral of f of z is equal to z plus 1 over the straight line curve in the complex plane from the point I to the point 1. So first, if we're starting at the point I and we're ending at the point 1, and we have a straight line path between them, so it's this line segment right here, I want to integrate f restricted to that line segment. And so I need to come up with a parametrization of that. Here's where it's useful to remember the convex combination approach for straight line paths. So we should write down z of t is equal to our starting point, which is I, plus t times our end point minus our starting point, so I minus 1. And then it's going to be useful to know z prime, because we're going to use that in the formula. So z prime of t is going to be equal to just I minus 1. And if I use the definition of the integral over c of z plus 1 dz, so this curve right here is our contour c, then what am I supposed to do? Well, I guess I got to tell you the values of the parameter as well. It's not fair to give you a parametric equation and not tell you the parameter values. This should be the integral from 0 to 1 of the function z plus 1 with the function composed into it. So that's going to be I plus t times I minus 1 plus 1. There's the function z plus 1. So this is z plus 1. And now what am I supposed to do? I'm supposed to multiply that by z prime. Well, z prime is I minus 1 times dt. And so what we've done is we've reduced this complex integral on the curve into a simple real integral on the curve. And now, because that sorts into real and imaginary parts, I can just integrate it using the regular old theory of real integrals. So if I do some algebra here, and I separate the real and imaginary halves in order to use the algebra that to use real calculus, technically I'm supposed to sort this explicitly into real and imaginary parts. So if you expand this all the way out and you sort it into real and imaginary parts, then you end up with this. So a whole lot of algebra happens. So what do I mean by algebra? I mean, this all needs to be expanded, and then a real part and an imaginary part need to be sorted out at this point. What you end up with is the integral from 0 to 1 of 2 minus 2it dt. And if you integrate that, you just get 2 minus I. Having set up a basic notion of line integration in the complex setting, we should talk a little bit about the sorts of curves that we want to integrate over. One of the most basic things that we might ask is that a curve be closed, which is to say a curve is closed if I start moving on the contour and I end up where I started. So a closed curve is just a loop of some kind. So closed curves don't eliminate the possibility that a curve might be self-intersecting. So this is simple. No, it's not simple. This is an example of what's called a simple closed curve because it doesn't intersect itself. It's also possible that you could have a closed curve that looks like this, where you've got a self-intersection. So this is closed but not simple. Okay. Simple closed curves are the nicest sort of contours that you can get when you have a loop, beginning and end at the same point. Curves that do intersect themselves are topologically a lot more complicated, and so they're harder to deal with. So normally we eliminate the possibility of self-intersecting curves by requiring that the curves that we're working on are simple. As I mentioned earlier, curves come with the notion of orientation. So when I build a parametrization for a curve, so some function that describes how a particle would traverse that curve, I have two different possibilities. I can imagine traversing the curve in such a way so that the inside of the curve is to the left, or traversing the curve so that the inside of the curve is to the right, in the case of a closed curve, I mean. So if I had a circle, I have two different possible orientations, or two different ways of traveling around the curve. We're going to choose this to be the positive orientation, where I keep the inside of the region that I've wrapped up to the left. And this is going to be called the negative orientation, where as I traverse the curve, I keep the inside of the area that I'm traveling around to the right. It is sort of amusing to point out that this idea of inside and outside, and the fact that curves have an inside and an outside so that this notion of orientation makes sense, is the subject of a really beefy theorem called the Jordan curve theorem, or Jordan curve theorem. And the Jordan curve theorem basically says that every continuous closed curve has, or every continuous simple closed curve has an inside and an outside. In more high-level language, that you have an unbounded exterior, so that is like running out to infinity, and a bounded interior. It's sort of famously difficult proof for a theorem that seems so obvious. So if you want to amuse yourselves at looking at the intersection between complex analysis, set theory, and topology, you can go look at the Jordan curve theorem. We are going to just assume that when we write down an integral with around a closed curve, that we always mean that we're oriented in the positive direction. So that has a special symbol. So integrating around something like this, we'll use a circle to mean that the contour that we've traveled around is a closed contour. Okay. The other thing that we can do with curves is we can link them together into curves that are called piecewise. So it's also possible to have a closed curve so that the pieces of the curve are smooth, but maybe there's corners where they join up together. So another example of a simple closed curve, a smooth, or what would be called a piecewise simple closed curve. Let me make sure I haven't written that down. Yeah. Might be something like this, right? So you could have maybe a smooth curve and then a corner, and then another smooth curve and then a corner, and another smooth curve and then a corner, and another smooth curve. So this would be called piecewise smooth. Because even though it's not differentiable at the corners, aside from that collection of corners, the function is smooth. So you might call this C1, and this C2, and this part C3, and this part C4. C1, C2, C3, and C4 are all smooth, and they're not smooth where they link up, but as long as they join correctly, and there's only a finite number of them, well, I mean, we've got to be a little bit careful about that. I'm just going to say finite for now. A finite number of smooth curves linked together like this are a piecewise smooth curve. And it's very easy to set up the notion of what you mean by integration over a piecewise curve, because integrals don't care about single points. So if you have an integral over a piecewise smooth curve and you want to evaluate it using the definition that we had above, the way that you do it is you just yank it apart into the integral over the first piece, so this is C1 of f, plus the integral over C2 of f, plus the integral over C3 of f, plus the integral over C4 of f. So you just evaluate the integral on the smooth pieces and then add everything together. Normally in notation that's written as something like the sum is k goes from 1 to n of the integral of ck f of z dz, where n is the number of piecewise, or of chunks that you have in your piecewise smooth curve. Okay, so integrals can be defined on a single smooth curve, or they can be defined on sort of a bunch of them chunked together in pieces, as long as those pieces join up in the correct way. Okay, so let's talk a little bit about the fundamental theorem of complex functions. So first off, what does the fundamental theorem of calculus say? What does it do? So to remind you, the fundamental theorem of calculus, which is so important that it's called fundamental, gives you a way of evaluating definite integrals. So a definite integral in the real calculus interpretation is a way of describing the signed area underneath a curve. And what the fundamental theorem of calculus does, or at least part of it, is give you a connection between the evaluation of that number, like, and the antiderivative, which is the indefinite integral. And so it's a very, very useful formula for evaluating definite integrals, because it means you don't have to do Riemann sums or estimates or limits. You can just find an antiderivative and plug numbers into it. It's so important we don't even name it when we use it. We just do it all the time. Every time you take an antiderivative and then plug b and a in and subtract, you've used the fundamental theorem of calculus. So what the fundamental theorem says is that if you have a function f, which is the derivative of a continuous function defined on some interval, then this number called the definite integral of f between a and b is just equal to the antiderivative with a and b plugged into it and subtracting. So this is an amazingly useful computational formula. Amazingly useful. And it turns out, perhaps unsurprisingly, given that we keep talking about how complex analysis is just an extension of real calculus, that complex calculus also has a fundamental theorem. The hypotheses are slightly different, but they're chosen in such a way so that the pieces of the complex integral can have the real fundamental theorem applied to them. In fact, part of the reason why it's so useful is if I know that I can evaluate a complex function, I mean, what would we really want to be true here? We would just be living in the dreamland if it was the case. Maybe if we're really lucky, we'll be able to evaluate f of z dz over some contour. And if we were living in a universe where everything was nice, maybe it would be the case that if this was the point A and this was the point B, maybe I could write down f of b minus f of a, and I wouldn't even need to figure out a parametrization for the curve because I could just plug the 2 points in. That's sort of the dream. And it turns out to be the case that if we're careful about the sort of functions that we consider and the domains they're defined on, we can do this. We can just evaluate a complex integral by plugging in, finding an antiderivative and plugging in the beginning and end points, as long as we're careful about the hypotheses. So this is what we really, really want. We really want this to be true. The first thing that we're going to put as a hypothesis is that the functions are defined on what are called simply connected domains. Okay, so a simply connected domain is a domain essentially with no holes inside of it. So if I have a domain D, it's simply connected if there's no holes. So D as a subset of the complex numbers is simply connected if there are no holes. A more precise definition is that if you wrote down a function inside that domain, like a curve inside that domain, like this, any curve that you write, any closed curve that you write inside should be able to be continuously pulled back or shrunk to a single point. Now I can't do that if there's a hole in the way because I can't bend the curve around the hole. So if I could take this and I could collapse it and collapse it and collapse it down to a point, sort of pull the function through without leaving the domain, then the function is simply connected. All right. So what's an example of a domain that's not simply connected? A really irritating not simply connected domain would be something like this. So you have an open set, and suppose that there's just a hole in it. So maybe this part of it's not here. So this domain is not simply connected. Because if you drew a loop around in this domain that went around the hole, so say there's a loop here that goes around the hole, there's no way that you can pull that loop into a single point without leaving the domain. Anytime you tried to do it, you'd have to go through this little circle right here. And going through the circle means you've left the domain because those points aren't inside D. So simply connected domain essentially means it's a set with no holes in it. And the most irritating non-simply connected domain is this one. So take a circle, which is simply connected, and eliminate a single point. So you have some point inside here that's not there. So remove a single point. This is not simply connected. Other examples of simply connected domains might look like this. So this domain is simply connected. They don't have to be circles. Okay, so again, without going into the technicalities of the topology, a simply connected domain is a domain with no hole inside of it. Okay. So that's going to show up as a hypothesis in our theorem for the complex fundamental theorem, is that the domains the functions are defined on are simply connected. Okay, so it's worth remembering what the hypotheses were for the real fundamental theorem of calculus. For the real fundamental theorem of calculus, we required that f is the derivative of a continuous function, capital F. For the complex fundamental theorem of calculus, we're going to require more. So we start with a continuous complex function f. We need it to be the derivative of an analytic function. So this function needs to be analytic. Remember that analytic here means infinitely differentiable. On a simply connected domain D. So that's going to be our replacement for the idea of an interval, is that this is simply connected. And then the idea is that if we have that, if we have a function that is the derivative of an analytic function, and so that means we have capital F prime of z is equal to little f of z for all z in this domain, then any contour integral that we set up inside here can be evaluated just on the endpoints, just like the real theorem says. So the idea is, if we have a continuous function that is the derivative of an analytic function, and the domain they're defined on is simply connected, so no holes inside of it, then you can not even bother with parametrization. You can just directly evaluate by taking the antiderivative and plugging in the endpoints. So this is an amazingly powerful theorem. So to reiterate, the relationship with the complex fundamental theorem says that f is continuous and f is analytic. Then you can do exactly the same game. A continuous function with an analytic antiderivative defined on a simply connected domain follows the fundamental theorem of calculus. You might actually recognize that this is connected to the idea from multivariable calculus of path independence. So when you study multivariable calculus, there's an entire class of functions, vector fields, for which you integrate a function against a contour, and it doesn't matter how you start and how you end, or it doesn't matter how you get from A to B. All you care about is where you started and where you ended. And so this is connected to ideas, again, so this is the second time we've mentioned this, related to ideas of conservative vector fields, which are very important in physics. For example, the work that you do in a gravitational field does not care where you begin and end. It only cares about where you started and where you ended, which again sort of justifies why it is that complex analysis shows up with such a deep connection to so many physical applications. Okay, so let's do a quick example. I'm not going to do the proof of this right now. What I want to talk about is the function that we talked about before. I'm going to show you how the fundamental theorem of calculus could have been used to evaluate our previous integral. So recall that we had the integral of z plus 1 dz from z equals I to z is equal to 1 on a straight line path. So we've started here at the point I, and we ended at a point here at 1. When we did this before, we set up a parametrization, we plugged it in, we had to do all sorts of algebra to sort things, and we ended up with, let's see, go back up here and take a look at it real quick. So there would have been a lot of algebra involved here because I had to parameterize the path from I to 1. I have to then plug in. I've got to take this chain rule derivative, evaluate everything in terms of the parameterization. Using the fundamental theorem of calculus, well, this function, f of z is equal to z plus 1, is certainly continuous. And it's also the case that I know what its antiderivative must be because it's a polynomial. I can just integrate it. So capital F of z is equal to z squared, 1/2 of z squared plus z. That is definitely an antiderivative of this function. Has f prime is equal to little f. And because capital F is a polynomial, it's obviously analytic. Capital F is analytic everywhere. And the whole complex plane is simply connected. So that must mean it does not actually matter how we get from I to 1. The fundamental theorem of calculus applies here. So the integral over this contour of z plus 1 dz must be equal to capital F of 1 minus capital F of I, which is equal to 1/2 of 1 squared plus 1 minus 1/2 of I squared plus I, which is 1/2 plus 1 plus 1/2 minus I, which is 2 minus I. So the fundamental theorem of calculus is an incredibly useful tool for evaluating these things that allows you to avoid having to work with the parametrized paths as long as the function is analytic on a simply connected domain containing the curve. Now, the most interesting questions are going to be those questions for which that is not the case, but when we can do this, we definitely want to. And the fact that the fundamental theorem of calculus holds is going to give us some remarkably useful facts about the behavior of functions around closed loops. And so what I'll do in the next video is we'll go through some examples, a very important example that points the way to something called the Cauchy-Goursat theorem. And so as a way of prodding you to think about what the implications of this are, I have a question. So here's a question. What is going to happen to a function that looks like this? What if f is analytic on a simply connected domain and you integrate it around a closed loop contained in that domain? So we have some simply connected d. We have a function f which is analytic on d. And I have some loop contained inside of d that's simple and closed. So here's c contained inside. What should that be? And that's one of the sort of central insights about the behavior of analytic functions, and one of the key tools that we're going to use to develop the theory of the sort of extended theory of integration of complex functions and way of probing the structure of such functions. All right, so the next time what we'll talk about is a very important couple of examples, and then I'm going to actually sketch out the basic ideas of how the proof of the fundamental theorem works, because the proof of the fundamental theorem essentially boils down to being able to invoke the real fundamental theorem. All right, so I'll see you guys next time.